Assalamualaikum warahmatullahi wabarakatuh and hello. Uh, my name is Muhammad Fakri Fasib Hisham. My metric number is 1565 and today we will presenting about our project horizontal plate lifting clamp. Our group members include Muhammad Aidil Muhammad Nizam 214-243, Muhammad Zafran bin Muhammad Yunus 215-633, Muhammad Akif bin Zulkifli 215710, Muhammad Jahid Iskandar bin Kamarun Nizam 215866.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akil bin Zulkifli. My metric number is 215710 and today I will give a little bit introduction about our project, which is horizontal plate lifting clamp, which is a device to lift and move metal plates in a horizontal position. So basically our product have five components, which is clamp body, clamp handle, clamp base, clamp arm and clamp holder. So the project involves 3D design, structural analysis and fabrication using 3D printing and CNC machine. So CLC or stereolithography was used the main part because it is light and easy to 3D print. Then the base is made from aluminum for better strength and support. And this project is integrate engineering theory and practical skill, covering the full product development cycle. So now I will continue with our specification of our project component. So there is four part that is we choose to produce it with SLA or 3D printing because it is rapid prototyping abilities, cost effectiveness, and ability to produce complex geometry without the need of extensive extensive tooling. So for the holder which is part that will hold the plate, then the body is part that hold all the part of the clamp, and then arm there is two part that will hold the holder, and lastly handle is where you hold you control the clamp using your hand. Last but not least, we use aluminum block by using CNC machine to produce our clamp base, and we use it because it is strong enough, high durability and resistant to corrosion.
So for the next part is the design principles. There are four things that are being discussed in design principles, which is the first one is design concept, next one CAD modeling design, and then material selection, and the last one is the finite element analysis. So for the first one, for the design concept, we develop a horizontal plate lifting clamp for safe and efficient handling of flat metal sheets. It is designed for use in metal fabrication, manufacturing, and construction industries. Emphasize on safety, functionality, and manufacturability. It also provides a firm grip on the metal plates while minimizing accident risk to happen. And then the features of this design is five main components, which are clamp base, clamp body, clamp arm, clamp holder, clamp handle enables and it enables easy for assembly, disassembly, maintenance, and also for the part replacement. So for the next one is the CAD modeling design. We use the SolidWorks CAD software for designing this object for high precision, and then the dimensions and the tolerances defines for accurate manufacturing and assembly. And we also use the aluminum based design with pockets, profiles, and holes for strength and fastener. And then the for the clamp body, arm holder, handle designed for SLA 3D printing, which is for the complex shapes, minimal post processing, and CAD use CAD used for simulation and virtual assembly checks in order to verify it is either fit and function or not. Next one is the material selection. So for the clamp base, we use the aluminum alloy because it is high strength to weight ratio and good corrosion resistant. It also excellent machinability, suitable for CNC milling. And for the other parts, which is the body arm holder handle, we use the PLA resin via SLA 3D printing. It is because why we use 3D printing, because of the lightweight and affordable, allows intricate shape fabrication, environmentally friendly, suitable for non-loud bearing components. So the last part is for the finite element analysis. So there are three things that we got from doing the analysis, which is the stress analysis, strain analysis, and displacement analysis. For the stress analysis, as you can see in the picture above, this is the stress analyzing diagram of the clamp body, reflecting the comprehensive stress state inside the material itself. The maximum stress is 4.451 megapascal, which is much lower than the yield strength of the material, which is 225 megapascal. So the structure is very strong and sufficient. So next one is the strain analysis. For the strain is mainly concentrated around the cutout regions and corners of the base. Higher localized deformation occurs where geometry changes sharply, and the majority of the structure shows low and evenly distributed strain. This indicates material is not undergoing significant elongation or compression across most area, and this confirms the design effectively managed the applied load. The materials operates within elastic limits, reducing risk of permanent deformation or failure. And also the strain results confirm the clamp is structurally stable and safe under expected forces. And then for the next one is the displacement analysis. So it shows how much different parts of the clamp move under applied load, as you can see above. And it is low displacement occurs near fixed support. The higher displacement seen in areas that are more flexible or less supported. And the color scale helps visualize movement, that blue for the small displacement and red for the larger displacement. These results ensure the design won't bend or shift excessively during use, helps guide design improvements for better stability and reliability.
Next, we will go to the process flow of clamp fabrication. Firstly, the design stage. The drawings include each part specific measurements and tolerance, which are crucial for obtaining the maximum level of precision in the manufacturing process. Furthermore, because each component's CAD model specific dimension, it may be used for simulation and virtual assembly design. Next, a structural simulation was run on the aluminium foundation to examine stress distribution under the imposed load. The FAA confirmed that the part could withstand the required force without failure, ensuring its safety and performance prior to manufacturing. Next, the CAM process was carried out using SolidCAM, which is incorporated into SolidWorks. The objective was to transform the 3D CAD model of the aluminum base into precise machine instructions, which is G code, for CNC milling. Next, the clamp aluminum base was produced using a MZ 5-axis CNC milling machine, which enables for high precision cutting with different angles of approach in a single setup. SLA or stereolithography 3D printing was used to create the clamps non-load bearing components such as the clevis pin and the linkage arm. This process offers exceptional precision and a smooth surface finish, making it ideal for intricate pieces with complex geometries. And lastly, following the CNC machining and SLA 3D printing processes, all components were post-processed to improve surface quality, ensure dimensional correctness, and prepare for final assembly. And all components were manually assembled according to the design. Fasteners were inserted, which is the bolt and nuts, and alignment was verified. moving parts were tested to ensure proper mechanical function and smooth operation.
Next, for the detailed manufacturing process, for our project, the manufacturing process was carried out in a series of structured stages to ensure the functionality and the precision. First, we started with the design and CAD modeling using SolidWorks. So each component, such as the base and arm and the handle, was modeled with specific dimensions. The 3D models also help us simulate the assembly process to avoid any misalignment. Next, in the material selection stage, we choose aluminum alloy for the clamp base due to its strength and machinability, while the rest of the components were made using the PLA resin through SLA 3D printing. Then we perform the finity element analysis or FEA on the aluminium base. This simulation helped us check if the part could withstand stress during the real world use. And finally, we move to cam preparation, where we generated tool paths using solid cam for CNC milling and use it to prepare the files for 3D printing. So moving on to the next slide, after completing the digital preparation, we move on to the fabrication stages. In CNC milling, we use a 5-axis Mazak machine to machine the aluminum base, ensuring precision cuts and drill hole as designed. For the remaining parts, we use the SLA 3D printing with UV curable resin. After printing, the parts were cleaned in isopropyl alcohol and cured under UV light for added strength. In the post-processing stage, we deburred the aluminum parts and lightly sanded the printed components to ensure proper fit and safety. After all parts were ready, we manually assembled the clamp, aligning each component and checking for smooth movement of the handle and arm. Finally, in the testing stage, we applied a simulate load to ensure the clamp could handle the real-world forces. So everything fit well, operated smoothly, and passed all the performance checks.
For the discussion part, the modular design allowed easy assembly, maintenance, and also part replacement. SLA 3D printing enabled fast, cost-effective prototyping of the clamp body and also the handle. CNC milling of the aluminum base provided strength, rigidity, and also durability. Aluminum was chosen for its lightweight, corrosion resistant, and also good machinability. The FEA simulation confirmed the clamp could withstand expected loads, with minor stress concentrations identified for future improvement. The design successfully combined functionality, manufacturability, and also safety, making it suitable for industrial application after further refinement. The hybrid manufacturing approach merged structural strength (CNC) with design flexibility, which is SLA achieving both form and function. The combination of CAD, CAE, and CAM tools ensured efficient and integrated design to fabrication workflow. The physical prototype testing validated the simulation results with smooth mechanical operation and also proper part alignment. So, for the conclusion, the FEA analysis confirmed the aluminum base remained within safe stress limits, and the displacement output error due to unit or boundary condition issue and real-world behavior showed negligible deformation. So, the hybrid manufacturing, which is CNC and also SLA 3D, provide both strength and design flexibility, and the accurate assembly and smooth mechanical operation validated design tolerances and also fabrication methods. So it demonstrates the successful integration of CAD, CAE, and CAM tools for rapid development, and also the design met goals for safety, strength, and manufacturability, with room for future improvement in simulation and also accuracy and sustainability.